Okay guys, this is the atomic structure video for November 6th for my chemistry classes. And this is Miss Carr, and I'm away for a training, but I wanted to leave you guys with a bit of information on some questions that were missed on the pop quiz last week, as well as the composition of the atom notes. Now, at any point in time, this video can be stopped or rewound, and you can cover this information at whatever speed you feel is necessary. The video will be about 10 to 15 minutes long, and it's going to cover everything you need to know about atomic structure for the basics of this class. And this video will, of course, be uploaded on the website, one for the sub to show, but also I will leave it up so that you guys can review it. Now, quite a bit of the information in this particular video is going to be reviewed for you because the atomic structure is a topic that you guys have had covered in science classes before. And I recognize this, and that's one of the reasons that I saved this for the days that I would be out. So I want to make it very clear that if I seem to go a little fast, it's because I know that you guys have the ability to rewind or pause and get any notes or information that you may need. So we're going to first start off with probably one of the most missed questions on the pop quiz, and that is what is the modern model of the atom? That is the quantum mechanical model of the atom. You have electrons that are being treated as waves, that's energy, instead of particles, which is matter. So the Schrodinger equation, which is the equation that I showed you that was long and complex, and I told you that you wouldn't have to memorize it or know how to work it or know what the variables were. But you do need to know that this equation exists. And it was developed by Erwin Schrodinger in the 30s and 40s, the 1930s and 40s, and that this waveform equation, that when you solved it, it gave us an idea of where those electrons could be found around the atom. And that is those probable locations of the electrons. So when we talk about our orbitals and we talk about our sublevels, this is all coming from this quantum mechanical model. So this is kind of where we're starting from. Now, a lot of the images that you're going to see in the next few slides are not of the quantum mechanical model of the atom, or rather of the Bohr model of the atom, which is a planetary model. The reason for this is that it's really just easier for us to kind of look at and see and understand the pieces of the atom when we can actually look at electrons rather than looking at probability clouds, which are a lot harder to illustrate, for example. So I don't want you to think that these Bohr model illustrations are really what atoms look like. Atoms look a lot more like this over here, where you have this probability cloud of where the electrons may exist around a central nucleus. I'd like to start off with the simplest of our reviews, which is what an atom is. Of course, atoms are pieces of elements, and elements are those simplest forms of matter that can exist under a normal laboratory condition. Now, keep in mind, we can break an atom apart. It's not as indivisible as Democritus or Dalton once believed, that we can destroy an atom, we can take an atom apart, or we can smash atoms together, but those aren't normal laboratory settings. You're not going to see that in 99.9% of all labs all over the world. So atoms are the smallest particle of an element that still retains the properties of that element. So we're talking about when you get a single atom of gold, it's the same as all other single atoms of gold. So that is the smallest part of an element that we can recognize as that element. Okay, so we know when we're looking at an atom of gold that this is an atom of gold, and we'll talk about how we know that here in a minute. So onto the composition of the atom. Again, this model over here is the planetary model, the Bohr model of the atom. So just keep that in mind when we're looking at it, but it does show us the basic three subatomic particles that you do find in an atom. Of course, the neutron and the proton, both particles that you can find in the nucleus, and the electrons, which are the very, very tiny particles that, or waves rather, that we can find orbiting that nucleus in an electron cloud or a probability cloud. So first we're going to talk about the nucleus. The nucleus is the area that we find in the center area of the atom. It contains all of the protons, those are the positively charged, and the neutrons, which are the neutral charge or no charge. Then the nucleus does compose 99.9, and we could keep on going with those nines if you wanted to, 99.9% of the mass of all of the atom. So these are incredibly dense areas of the atom. In fact, if a nucleus were the size of a ping pong ball, it would weigh something like a car. So we're talking about something that is incredibly dense and incredibly massive on a relative scale. It is positively charged, and we'll talk about why here in a second. It is tiny compared to the atom as a whole. So the volume of the atom is mostly taken up by the electron cloud, and the nucleus takes up very, very little of that space. This is why the Rutherford experiments were able to demonstrate that most of the atom is essentially empty space. The next step is the electron cloud, and this is that probability field that we talked about with the quantum mechanical model. And this surrounds the nucleus and contains all of our electrons. It has almost no mass, but it comprises almost all of the volume of the atom. It is negatively charged, and it's defined by these probability barriers that we discussed with the Schrodinger's equation. So we can discover where those electrons are most likely to be found. We're going to go through the subatomic particles relatively quickly. I think most of you are very familiar with these, but in case you aren't, this is a good chance for you to review and maybe learn a little something that you didn't know before. The first is that the symbol for a proton is a P with a little positive charge on the upper right-hand corner. This shows that it is a proton and that proton carries a positive charge, which is, of course, the indicator that you have a proton. It is located in the nucleus, and this may come as a surprise, but all protons are identical. It doesn't matter if you're a proton in a gold atom or the proton in a hydrogen atom or proton in a carbon atom. They're all identical. The only difference between elements that we see is the number of protons that they have. The proton has a mass, and this is a unit that you need to be familiar with. This mass is called an atomic mass unit. So it's also referred to as an AMU if you are abbreviating it. So this is the mass of one atomic mass unit is the weight of one proton. So when we talk about AMUs, you're talking about how big a proton really is. The subatomic particles, the second of our subatomic particles is the neutron. The symbol is N with a little 0 superscript. It has no charge. It doesn't have a 0 charge. It doesn't have a lot of people think, neutral charge. No, a neutral charge is the same thing as saying that there is no charge. So there's not positive, not negative. It has no electronic charge at all. It is located in the nucleus, and it has about the same mass as the proton, so around 1 AMU. And we refer to neutrons and protons as the same relative mass. So when you talk about the atomic mass of an atom, you're talking about the average of the number of protons plus the number of neutrons in that atom. And the last of our subatomic particles is the electron, by far the most exciting of our subatomic particles, as well as one of the least understood, and we're still kind of learning to understand about it. So what we do know is that we write it with the symbol E with a negative sign, a negative superscript. It is negatively charged, and it moves around the nucleus in that electron cloud, in that probability field. And its mass is around 1,840th of an AMU. So that gives you some idea of what kind of mass we're talking about with this particle. with a very, very, very tiny, tiny particle. So it would take 1,840 electrons to make up the mass of a single proton or a single neutron. Okay, and the next thing we're going to talk about here is the numbers of protons, neutrons, and electrons in the atom. The number of these subatomic particles tells us everything about the way an atom or an element is going to react. And you need to be aware that in a normal atom, that is an atom with no charge, the number of electrons and the number of protons are going to be equal. The reason for this is that normal electrons are electrically neutral. So you can't have a positive or negative charge. And so the number of neutrons doesn't have to be equal. The number of neutrons has no effect on the overall charge of the atom. You can add as many neutrons as you want to a limited extent, and we'll talk about isotopes more in a minute. Most of the time, you're going to have more neutrons than you do have protons, but it's generally a fairly close number. Usually 1 or 2 or 3 more neutrons than protons, but the number of neutrons doesn't have any effect on the overall charge of the atom. So again, your protons and electrons are going to be equal in a normal atom. The number of neutrons does not have to be equal. So let's take a look real quick in summary about our subatomic particles and the structure of the atom. And I put all of this into a chart, and I do recommend that if you don't have time to get all of this chart information down in the video itself, that you go ahead and pause the video so that you can get this information into your notes. So here's the summary of those subatomic particles. Of course, you have the electron. The symbol is E with a superscript negative sign. It has a charge of a -1. Its mass in atomic mass units is 1 divided by 1,840, and its location is within the electron probability cloud. Your proton, as a subatomic particle, has a symbol of a P with a superscript positive sign, and it has a +1 charge. It has a mass of 1 atomic mass unit, and its location is within the nucleus. And the neutron has a N with a 0 superscript. That shows that it has a 0 charge, or no charge. The charge is 0, and the mass in atomic mass units is 1, and its location is also within the nucleus. Now, I have another video to follow this up where I will talk about the atomic number, the mass number, as well as a review of isotopes, which is what our lab on Halloween was all about. So we're going to put that into a separate video so that I can upload this and have more manageable file sizes. And I hope that once everybody gets these notes down, that we can move on to that next video. Thank you.